Well, here we are again. Today we want to do something pretty exciting and fun, so I think you'll like this. We want to take equations that have exponential and logarithmic parts to them. Might be exponentials, might be logarithms, might be both, maybe not. And solve them, find solutions for them. And we're going to do that by using the properties of exponents and the properties of logarithms. Nice. Okay. Here, let me show you the properties here, just as a little bit of a reminder. We've seen these a couple times new, but they're, now, but they're still kind of new. This number 3, 4, and 5 are the ones that we tend to use the most. But up here, remember we had the base A logarithm of 1 is equal to 0. Change that over to exponential form and you'll see why real quick. Have a base to a power A to the 0, and anything to the 0th power is 1. So that would be right there. All right. Number 2 is very similar. Again, taking the logarithm, changing it to exponential form. If I take base to the power A to the first is clearly A. So those two make perfect sense. But that kind of illustrates something of what we want to do here. Very often, if you have a logarithmic equation, it's useful to change it over to exponential and vice versa. Okay. Number 3, 4, and 5, again, are pretty important because that would be the product rule. Whenever I am taking the logarithm of a product of two things multiplied together, I can break that apart into the logarithm of the first plus the logarithm of the second right there. All right. The second one is the quotient rule. And we've seen that the logarithm of a quotient, B over C, is equal to the logarithm of the first one minus the logarithm of the second one. So that's good stuff. And then finally, we have the power rule, power to a power, whatever you want to call it. I guess not power to a power, that would be the exponential rule. But when I have a situation like that, when there's an exponent of a base and we're taking the logarithm of it, perfectly fine to take that exponent and drop it down on the ground in front. Now, there is this little caveat here, this little extra wrinkle. If the base of our logarithm is really a to the n, then we need an n underneath here when we do that. We have to divide that. This exponent and that exponent work together and turn into that. Okay. Why would you possibly want to do that? What if you had a base 8 logarithm, or let's go base 100, even better, of something? Okay. And see how I could rewrite that as the logarithm of 10 squared. I've got I've got common logs on my calculator, right? So sometimes you could take a weird base and change it into a regular base by expressing it as a exponent. And so in that case, something might happen. I think for the most part, you could ignore this and ignore that and be just fine. All right. Take the exponent, park it down in front. But if your base is the base of the logarithm is a to the n, then you should put an n down there. I mean, you have to put an n down there. Okay. Here, this one's kind of nice, kind of weird. If you have a base A log of B, you can switch A and B if you invert it over like that. Um, again, maybe if this is the 10 or an E or something, then you could switch it over. That one's kind of tied in with what we're doing here, though, with and I'm gonna mark number 7 because this is our change of base rule. And again, since we only have base 10 and base E logarithms on our calculator, getting down to a thing that we can push a button for and get an answer for is pretty handy. In this case, P would be the new base. And again, that's probably either going to be 10 or E because those are the two we have. But if I take the log of B over the log of A, then in whatever base I want to go to, then that's a change of base and I can punch it up. Right here, this one's handy. If I have an exponential where the exponent is a logarithm, essentially I'm raising a to a power that says, go get me the exponent. And that's going to be the exponent, not the exponent, is the argument of this logarithm. So effectively, the the exponent, which is a logarithm, and the exponential, which is a logarithm, are going to cancel each other. That didn't make a whole lot of sense, but you can kind of smite those out, and you're going to end up with just the b there. Very similarly, and I'm not real sure why they didn't write it, if I take the logarithm of a to the b, then again, the log and that exponent are going to cancel out, and I'll just have b. So those are kind of handy there, but it's mostly 3, 4, and 5, and then 7 if we need to do something on our calculator right there. Let me show you what I mean. Here are a couple examples right here, and the rules are we can use the um, properties of exponents. We can use the properties of logs. I don't know what I'm trying to write there. And we can also do regular old algebra. So pretty much anything we want, as long as we do it to both sides. Do the same thing to both sides, we're okay. All right. And those are kind of the tricks that we're doing. But and then again, very often it's very handy to take let me go with a to the b, that would be an exponential, and turn that into a logarithm form. Um, and doing the going back and forth on that. Let me show you what I mean. Right here in this first one right here, I have base 2 and base 2. I I don't really need the base 2. I need to get at this x minus 1 and the 2x. So one thing I could do here is the same thing to both sides. Namely, I could take the logarithm of both sides like that. Now I've got the logarithm of a base to a power. So I could use the power rule and take that x minus 1 out front. I'm going to put it in parentheses here just to make sure it stays together, and have the log of 2. And over here, I could apply the power rule to this side, take the 2x out front, and here's a log of 2. Now, I chose to do this with the common log, base 10 log, but you could also use the natural log. You could use anything. You could actually use base 7 logs here if you wanted to. It doesn't really matter. As long as you're doing the same thing to both sides, that's perfectly mathematically legitimate. You're trying to do that with the object of moving toward finding a solution. All right, and any base would do that here. Notice that now I have a log 2 on the left and a log 2 on the right. So if I divide the left-hand side by log 2, that's just a number, right? We could get a number for that off our calculator. I got to do it on the right as well. It's going to cancel on both sides. And now I have an expression that looks like something we started this semester with, x minus 1 equals 2x. I could come in here and add 1 to both sides. I'm sorry, let's subtract x from both sides. X minus x would get all the x's off the left, put them all on the right, would look like that. I would be left with negative 1 on the left-hand side, and a 2x minus x would be x. That is my solution. We just found a number that satisfies this equation up there. That's what we're trying to do. Okay? Here's another one. Let's try the same old trick here. Let's just take the logarithm of both sides. I'd have log of 256 equals log of 4 to the x minus 5. I could have used any other base. In fact, we did the last one with common logs. Let's do this one with natural logs. So I'm going to replace that with ln. And now we're working in base E. Okay. Everything canceled over here. It's not going to cancel in this one. So if you choose log 256 equals log 4 to the x minus 5, then you'd be working in base 10 instead of e. Doesn't matter. As long as you do the same thing to both sides, you're fine. All right. On this right-hand side, I'm going to use the product rule and bring that x minus 5 out front. Let's copy the left-hand side. Ay, ay, ay. And then I want to take that x minus 5, bring it up front with the product rule. Got the natural log of 4. Okay. Trying to get at that x. It's right there. Some point I'm going to have to add 5 to get rid of the negative 5 there, but I got to get rid of this natural log of 4 that's multiplied there. So the opposite would be to divide by the natural log of 4. That'll cancel. Got to do it to both sides, though. So I'm here. I'll have the natural log of 256 divided by the natural log of 4 equals x minus 5. And now I can come through there and add 5 to both sides, which will cancel that 5 off. I'm trying to get x, same old thing, trying to get x by itself. And we're just using the rules of algebra, and now also adding in the rules of exponents and logarithms to do this. My calculator will give me a value for this. I could have the natural log of 256, close up your natural log there, divided by the natural log of 4, close that up, and add 5. And we get a 9. Okay. Just for kicks here, just to make sure we understand this would work, I could have chosen up here to use the base 10 log, common log, and that would have changed all these natural logs to regular old logs. And when I punch that in, I'd have log 256, close it up, divided by the log of 4, close that up, and add 5, and I still get 9, right? I'm going to get the same answer either way, but that's what we're looking for there. All right. So you got to know these rules pretty good to know what your options are here. But that power rule is pretty handy, and the product rule and quotient rule. I got some of those coming up too. Right here, what can we do with this? Well, there's a couple things we could do. We could take the log of both sides and then bring down the exponents. That's not going to they don't have a log 8 on the left and a log 16 on the right. So that's a little bit different. It won't work out too well. But there is this handy little trick. Check this out. What if I rewrite 8 as 2 to the third, and then that is raised to the x plus 2, and 16 would be 2 to the fourth, raised to the x plus 1. Okay. At that point, here, those rules of exponents apply, and I do have an exponent raised to an exponent, a power to a power, so I can multiply those powers, and I'll do it slow motion here. Would look like that. This one's going to look like this. I would probably distribute that out. That's a 1 there like we had. So that you had 3, had 3x plus 6, and over here 4x plus 4. Okay. Now if I take the logarithm of both sides, and we'll switch back to the common log just for variety here. Now if I can spell a 3-letter word here, you can see that the power rule would apply. So I could take this exponent and park it, 3x, I can read it, log of 2 equals, I'm going to take the exponent here, use the power rule to move it down onto the ground, log of 2. And now I have a logarithm of 2. Divide both sides by the log of 2. Those are going to cancel. It's on the left, it's on the right. I can cancel it. And I'm left with 3x plus 6 equals 4x minus 4. I want to gather all the x's on one side, all the constants on the other side, and isolate x. I see that there's 3x here and 4x there. So I would probably subtract 3x from both sides. And that will cancel it on the left-hand side and leave me just a single x. 4x minus x would be an x here. Okay. Incidentally, up here, I probably should have made sure I put this in parentheses so that it was clear that that log 2 was off there all by itself. But that's fine. What else we got to do here? Got to get this 4 off of this side. So I would simultaneously subtract 4 from both sides. Plus 4 minus 4 cancels. 6 minus 4 is a 2. And I've got my solution there. Okay. So that's a good trick to watch for. If you can see that you have an exponential on both sides, and this is a power of 2, say this is a power of 2, maybe power 3, 5, whatever, but that's a pretty handy trick to do. Rewriting that base as a smaller base to a power, that'll let you move that power up with the rest of the power and then bring it out front. Here's another one. Doesn't seem obvious at first, but here's a 2 and there's a 2. And the trick on this one would be to rewrite it, leave the left-hand side alone. But I could write this as 2 to the 1/2 power, like that. Okay. Now, if I come in here and take the natural log of both sides, or the common log, the power rule would let me bring those exponents down, and I'd have 5x times the natural log of 2 equals 1/2 times the natural log of 2. And I could cancel those natural logs of 2. And I could divide by 5 here. Cancel this one. That'll leave that x sitting there all by its lonesome self. And I'd have to divide by 5 over here. And I'll have 1 over 10. You could leave that as a fraction. You could write it as a decimal, 0.1, whatever you're in a mind to do, whatever seems better. But that one's not too hard either. Once you've got those rules of exponents, rules of logarithms, and regular good old algebra, and work to find a solution. Now, sometimes there's not a solution. Okay, and I've got an example here. Sometimes things just don't work out. What they've done here is they created an exponential equation where 3 raised to the x plus 1 power is equal to -2. And so what they did was they said, well, let's graph this side. And you can see the graph there of that. A regular exponent would cross down here 0, 1. But we've shifted it, haven't we? And we magnified it and stuff. So this is kind of up there. Anyway, that blue line shows the left-hand side of the equation. Meanwhile, on the right-hand side, this -2, if I graph that, I get this line down here. And we're looking for a point that lies on both of those lines, a point that satisfies both sides of that, or a point that satisfies the entire equation here. You can see that the blue line never gets down to the red line. They do not cross. There is no solution. So sometimes that's just the way it breaks, you know? And particularly here, it says watch your positives and negatives. This top has a range of 0 to infinity, right? And this one has a range of -2. And there's nothing that is shared there. If we didn't have the negative sign, here's a slightly different problem. Here's a 3 raised to the x plus 1 equals positive 2. That would create a line that goes across here, and I would have a solution, okay? And I could find that, but you're not going to get one here, okay? If you wanted to do that one, take natural log both sides, common log, whatever you like, bring down the x plus 1 times the natural log of 3 equal to the natural log of 2. And then we'll divide both sides by the natural log of 3. That will cancel it on the left. And then I could subtract 1 like that to get this off. And now my x is by itself. And I very simply have x equals natural log 2 divided by natural log of 3 minus 1. And my calculator says that that has an answer. You move it up and you will, where'd it go? I'm working on that right there. 2, close, divided by natural log of 3, close, and subtract your 1. And there is a number there, negative 0.369. Can you see that that is slightly to the left of x equals 0? X equals 0 will be the y-axis here. And this point where we are is a little bit to the left of that. All right, I didn't draw it very well, but you get the idea, right? That's where we, that x value right there is the point that we're looking for. So you could find that. But the 3x plus 1, 3 raised to the x plus 1 equals negative 2. Those never meet. You're not going to have a solution. Can't solve it. There's no answer. Okay. Here I want to solve some exponentials with that have different bases, but again, not tricky. I see exponentials. I know switching to logarithms is a good option, or I could take the logarithm of both sides. And so let's do that here. I'll have the log of 5 raised to the x plus 2 equals the log of 4 to the x. Looks like it's time to use the power rule, and I'll have x plus 2, tie it up. Log of 5 equals, bring the exponent down, x log of 4. And now I can divide both sides by log of 5. And it'll cancel on the left, show up on the bottom over here. And that's just a dumb old number. Thanks. Sorry. Pen got crazy. And oh, there's all kind of things we could do here. But let's go ahead and process that. I don't know why that calculator's there and so big and all that. That's kind of got me stumped. But here's an x plus 2 equals an x times a number here. You could go ahead and get a number. Might be better to leave this one the way it is, though, as long as you can. And I'm trying to figure out if I got room to finish this or not. So in most things, a decimal approximation is probably going to be good enough. And you could go log 4 divided by log 5, like that. 0.861 would be a value of that. The more digits you put, the better. The best thing, of course, would be to leave it like this and to deal with it at the end. But if I did that, then I could put it over here, subtract it, bring it all together, get the x's together, bring the 2 over here, and divide by whatever coefficient I have. Let's ride it a little bit longer. And so I'm going to just put log 4 over log 5 right there. Do I have my pen going? Yeah. Log 4 over log 5. We'll bring it over here, kind of have to slump around the calculator. But I'm going to subtract that from both sides. Minus log 4 over log 5. Do that over here. And I had that X out there too, so that needs to be part of that. I put it on the back because normally we have number X, and so that looks a little more like what we're used to seeing. And all right, so that's going to cancel this on the right-hand side. I need to subtract 2 to get all my constants on the other side. And now that we've done all that, made a huge mess. Let's see what we've got. I've got X minus log 4 over log 5 times X equals -2. I've got a common factor of X in this thing. So let's pull that out front, and I'll have 1 minus log 4 over log 5. That's equal to -2. I could divide by all of that. And as long as you remember to close this up. Now we haven't made any assumptions. We haven't rounded anything off. We've got all those X's by themselves together, and I've got -2 divided by that super compound fraction there, and almost covered it up again. But what do we got here? -2 divided by, I'm going to put this in parentheses, 1, subtract log 4, close up the logarithm, divided by log 5. You can close that log if you want, close the whole fraction that we're dividing by. That's fine. You don't have to. It's at the end. And I've got a number. I've got a solution here for this thing, -14.425. Again, we're going to round this thing at some point. And as long, the longer you can put that off, the better. The more decimal places you carry, the better. Math people, you know, aren't usually doing anything with these numbers. They're just kind of working with the tools, trying to figure out how to solve these kind of problems. So they might even leave the log 4 over log 5. But I think that's a good place to leave that one. Okay. We've got another one here, and it's going to be a similar when you have these different bases. Okay. The, that makes things a little more cumbersome. I meant to go green here just to separate off there we go. Okay. Log of 2 to the x equals log of 3 to the x plus 1. Power rule says bring those guys down. Get them off the top shelf. I would have x log 2 equals x plus 1. Tie that up. Log of 3, like so. And I would get all those logarithms together because they're all just numbers, right? And trying to figure out what the calculator was saying. Is saying you could use logarithm, you could use natural log, you'll end up with the same answer, which is the answer that we got. So that's good. But yeah, let's come in here and divide both sides by log. I don't know. Let's get rid of this one. If I get rid of this one, I don't have to distribute it. I could have divided both sides by log of 2, but this way I only end up with that mess in one thing, not both. So once that's done, I'll have x times the log of 2 divided by the log of 3, and that's going to be equal to x plus 1. I want to get all of my x's together on the same side. Same old deal, right? So here, if I come in and subtract x from both sides, then that will happen. Minus x there, cancel that x, subtract x from the left-hand side, and now I'm looking at x log 2 divided by log of 3. equals 1. Oh, I lost my other x, minus x. Don't forget that one. Okay, there's a common factor of x, so I can pull that out front. And I'll have log 2 over log 3 minus 1. You can see that if I distribute that back, I'll be right there on top of that. And here's a 1 on that side. You could go ahead and get a number for this and take the inverse of that. That would work. Might be nice, though, just to, see what it is we're trying to put in the calculator. And there's lots of other options on how to do that and write that and everything. I'm not saying this is even the best way, but if I come in here and make it look just like it did there, I've got the 1 on top divided by, put some parentheses to hold all this mess together, got the log of 2, close up the logarithm, divided by the log of 3, close up the log, and subtract 1, close if you want, the denominator. You're going to get negative 2.7 for that solution right there. And I'll put a couple more digits here, but feel free to write as many of those as you can stand. Okay, or you could leave it like it is, right? If you were going to leave it like this, you'd probably want to combine the fractions here, which would involve getting a common denominator, which would be log 3. So this would go to log 3 over log 3. And then I could combine those fractions. I got the 1 on top, and now I've got a log 2 minus log 3 over log 3. That's a compound fraction, so I could invert and multiply, and I would get a log 3. You get the idea, right? Over log 2 plus minus 3, log 3. Okay. And, that should give me the same answer right there. We'll try it just to see if I'm insane, but there's the log 3 on top. We're dividing that by, get some parentheses around the whole denominator there, log 2, close, minus log 3 equals, there's that same number again. So maybe, if you were going to walk away from it and not turn it into a decimal approximation, that looks a little bit better to me anyway than this fraction of fractions of fractions. Do what you got to do. I don't know what to tell you. Okay. But you will get the same answer. All right, so here's something kind of stepping away from that one where we had exponentials on both sides. Sometimes they look kind of like this. You'll remember that this was our basic exponential growth model. So these are pretty handy for math modeling, biological modeling, economic modeling, interest rates, all of that kind of stuff. If I were looking at this, I see a dumb old number here, and there's a number here times an exponential. And I'm going, you know what? I could put those numbers together. All I'd have to do would be to divide both sides by 20. And then 20 over 20 cancels, and I will have 100 divided by 20 is 5 equals e to the 2t, like that. I got to get that t. It's an exponent. This exponential is holding me up. I need to get that t by itself. I could take the logarithm of both sides. So right here, we'll go log of 5 equals the log of e raised to the 2t. And then I almost missed it. This would work. I could do this. I could use power rule and bring down that 2t and put it down there, divide by the log e, log 5 over log e. That would work. Here's something that would be even better. Instead of doing the common log right there, let's do the natural log. If I take the natural log of both sides, I've got natural log of 5 over here. That's just a number. But here I've got the natural log of e to the 2t. And the natural log and e are going to cancel. And I'll just have natural log of 5 equals 2t. At this point, all I have to do is to divide by 2. And that's pretty quick work on the calculator. All I'd have to do would be ln5, close that up, divided by 2, and I've got a solution there. If this is time and we're thinking about radioactive decay, 0.8047 seconds or years or whatever unit we're talking about here. When you see that E, if you take the natural log of both sides, then that natural log and the base of E will cancel and save me some work. Here's another one, similar situation. Always trying to get these dumb old numbers by them, together before you go messing with the whole thing. If I can subtract 5 from both sides and cook this thing down, that's fantastic business. Okay, I would do that all day long. That's going to leave me 4 e to the 2x equals 12 minus 5 would be 7. Here's another number, another number. Get those together. All I have to do is to divide by 4, and that 4 will cancel. Come over here, 7/4, 1.75 if you're comfortable with the decimals. All right. Now I've got e to the 2x equals 7/4. I'm going to leave it a fraction as long as I can. And again, you could take the common log of both sides, but it'd be so much better to come in here and take the natural log of both sides, because I can do the natural log of 7/4 on my calculator. But over here, the natural log of e to the 2x is going to give me a 2x. And then all I have to do is to divide by 2, like so, and get a value for it. Natural log 7 divided by 4. We're done taking the natural log, and then I have to divide by the 2, which give me 0.2798. Okay. Whatever, the rest of that mess. You remember when we started solving equations and you could take the solution and plug it back in, make sure that it works. You could do that here too. That wouldn't be a bad thing at all to do. I won't do it, but you feel free to do that on your own work or right there if you want. Okay. Here's an odd one. I've got e to the 2x minus e to the x equals 56. And the thing up here at the top suggests that we could look at that like a quadratic. If I had some variable y to the 2 minus y, and let's go ahead and subtract 56 from both sides. Wow. 56 equals 0. Wouldn't that look like a nice little quadratic waiting to solve and factor? In fact, 56, I've got 2 factors, 7 and 8, that multiply to 56 and subtract to 1. So if I did y minus 8 times y plus 7, that would be the factorization of that quadratic right there. Now, that's not quite the quadratic we have, but check this out. I could take that e to the 2x and I could rewrite that as e to the x squared minus e to the x. Go ahead and subtract 56 from both sides, and it would look like that. And with that one, clearly, and here again, remember I've got a power to a power. So the power rule of exponents says you can multiply those, the power to a power, and just get 2x, right? So here I've got something squared minus something minus 56 equals 0. That's exactly what we have here. And sometimes you'll hear people talking about doing a U substitution. In calculus, we do U substitutions. We could do a Y substitution here. We can just come along and say, let Y equal e to the x. And then everywhere I see e to the x, I'm going to replace it with a y. So now I do have this equation. I do have that factorization. I could get the solutions for y. They'd be positive 8, negative 7. And then put that back over here and see what that would mean in terms of this. Okay. Let's not do that, but that would be an option. Right here, if I just factor this thing, I need something times something that gives me e to the x squared. So that would be e to the x times e to the x. Then I need something times something that gives me 56. Again, that's going to be 8 and 7. I see that the signs are different, and the big one is negative. So I get a negative there and a positive there that equals 0. And now multiplying two things, getting 0. So either the first one is 0 and or the second one is 0. And we can find solutions for that. Go ahead and add 8 to both sides. Do the same thing here, subtract 7. Kind of doing these at the same time. But would be super easy right here to come in, take the natural log of both sides. Natural log of e to the x is just x. And so my solutions are going to be the natural log of 8. Over here, I take the natural log of e to the x equals natural log of negative 7. The natural log and the e are going to cancel out, and x equals the natural log of negative 7. The natural log of 8 is 2.079. So there's a decimal approximation for our answer. Natural log negative 7. Okay, it doesn't like that. Why not? Well, remember my natural logs, all my logarithmic equations look like that. They don't come over here. Okay, so when you put that negative 7 in there, it doesn't know what to do with that. It's not a real number anymore. It's a complex number. So that one's not going to give us a solution right there. But we do have this guy. All right, just a couple more here. You can kind of see patterns starting with this, and we want to combine things, but that 3 and the 7 would combine very nicely. That gives me the 2 times the natural log of x equals 4. Clearly, I could divide both sides by 4, so the natural log of x equals 2. Look for all that stuff that you can combine and simplify before you go messing with the natural logs or the exponentials or anything like that. Okay. What I would do right here is I would take both sides and I would raise e to the left-hand side and e to the right-hand side. That seems like a really weird thing to do, but we did the same thing to both sides. I took e and raised both sides to the exponents that were there. Nice thing about doing that, e natural log are going to cancel, and I'll just have x equals e squared, and my calculator knows the value of that without even blinking. Right there's my e to some power, and I need e raised to the second power, 7.389. Okay, decimal approximation there. I could do a similar thing. What? I could do a similar thing on this one. I see a 2 right there that's just sitting there being dumb. Get rid of it. Okay. Now I've got the log of 6x equals 4. That looks better. Got rid of one thing. Right here, what could I do? Um, I could I could raise both of these sides to 10, and then 10 to the log, base 10 log of 6x would be 6x. Here's another thing I could do. Since this base is understood to be 10, I could take this logarithm and I could go to exponential form with it. So I could take base to a power equals the answer. Okay. We could have done a thing like that back here too. I would have had an e here, e to the second equals x, right? That would have been the same, would have gotten us to the same place. So 10 to the fourth is just 1, 2, 3, 4 zeros after a 1. That's 6x. I could divide both sides by 6. And I don't know what 10,000 divided by 6 is, but you can bet my calculator does, if I can find it. Where'd it go? There you are. Oh, good. My calculator's not happy now. Okay. Well, I'll work that out and see what the answer there would be and go with that. Oh, it's just mad about that last problem, I think. 10,000 divided by 6. Okay. 1666 and some stuff. 2/3. Okay. Got one more slide here. It's gone on a little longer than I intended, but here's the last of these. All right, so I've got some base 2 logs. Um, we don't have that on a calculator, but it's on both sides. I can do anything I like as long as I do it to both sides. How about we just cancel this base 2 log and that base 2 log? Okay. If you don't like that, just striking them out. Take 2 to the left-hand side equals 2 to the right-hand side and 2 to the base 2 log. Those are definitely going to cancel, right? So that would be another way to get there. That's going to leave me an x minus 1 equals 8. And I don't know anybody that can't figure that one out. That's going to be a 9. Okay. Last one here. Got log 3x minus 2 minus log of 2. What are we going to do? We got logs all over the place. Oh, wait a minute. Here, log minus a log, I could rewrite that as a quotient, right? So I could write this as the log of 3x minus 2 over 2. That will nicely simplify all this, and that's going to be equal to all of that. Okay. And then I could come in here and say I got a log on the left, log on the right. Just take those out. And now I'm down to a regular old algebraic expression that shouldn't give us any trouble. Multiply both sides by 2. I'll distribute that through here, 2x plus 8. Subtract 2x, I'll get an x over here. Add 2, I'll get a 10 over here. And so that would work right there. Got to know these tricks and the way to snake your way through them. But that's what we want to do. Thanks for sitting through that, and good luck with them, and bring a bunch of them to class, and let's see what we can do. Thanks. Have a great day.